Go into the cloud. Okay. Oh, I forgot. My page turned off. This week has been very morning. So chapter 15 homework will be due today, the 12th. The chapter 19 homework is due on the 19th. That's a week from today. The chapter 15 quiz is on Blackboard until the 17th. It's timed. You have 40 minutes, then it ends automatically. You have to do it in one sitting. You get one attempt. Make sure you have the time, and it's 25 questions. And the short answer questions will have to be graded manually. So your score may not appear immediately on Blackboard. And the chapter 19 quiz will be on the 19th. And you do not have SI today because David is out of town. I believe he posted something for you to view. That's why the chapter 15 quiz is online. So let's talk about some more things that we measure about the weather. So humidity is the measure of the amount of water vapor in the air. This is the property of the atmosphere that changes the most over time and place. And there's a few different ways that we can measure humidity. The simplest is, sort of the most basic is absolute humidity. Absolute humidity is just a measure of literally the amount of water vapor in a given volume of air. So you could measure it in grams per cubic meter, or in the US, it's commonly measured in grains per cubic foot, where a grain is very small. There's 7,000 grains in a pound. Why we use these random archaic units for everything, I do not know, but this is the case. Absolute humidity is very rarely actually used. You will not see absolute humidity listed places. Because it turns out what we experience as people is better expressed by relative humidity. The other way of representing the amount of water vapor content in the air is relative humidity. Because it turns out how we experience humidity can vary a lot depending on the temperature of the air for the same absolute humidity, the same amount of water in the air. So the most common way we express water vapor content in the air is in terms of relative humidity. This is not on. Things work better when they are. Relative humidity is the ratio of the actual moisture content in the air to the maximum moisture capacity of the volume of air at a given temperature. It's basically saying, okay, the air could hold this much water. How much of that space is filled up? So relative humidity is at 100%. The air is fully saturated with water. It can't hold any more. If it's at 50%, it's halfway there. Half the water it can hold is in the air. It can still hold another 50%. And relative humidity is the actual moisture content of the air divided by the maximum moisture content of the air, and then we multiply it by 100% to express it as a percentage. So relative humidity is a measure of how full the air is with water. So it's representing sort of the maximum, how much of the capacity to hold moisture is full. Which is why, and the reason that's very important to humans is because we primarily cool by evaporation. We sweat. If relative humidity is very high, there's not as much room for our sweat to pass into the air. We don't cool as efficiently. It feels awful. If relative humidity is very low, there's a lot of room for our sweat to evaporate into the air. We cool more effectively. So relative humidity has a big effect on what we feel and experience. So the amount of water vapor that air can hold is a function of temperature. The amount of volume of air at a given temperature can only hold so much water. The higher the temperature of the air, the more water vapor the air can hold, because the vapor pressure of water is higher at higher temperatures. I could go into more detail about that, but that's the general important thing. The higher the temperature of the air, the more water vapor the air can hold. And at higher temperatures, it's easier for water to remain in a gaseous state as a vapor. So warm air has a greater capacity for water vapor than cold air. If the temperature of a sample of air is lowered, if you cool air down, the relative humidity will rise. So for example, if you have something that tracks temperature and humidity, and you're in like a sealed room and the room cools down, the temperature will drop, the relative humidity will rise. And if you've got like one of those digital thermometers that also tracks humidity, that records it, you can just see it in the graphs. And eventually, if the temperature of a sample of air is cooled enough, the air becomes saturated. There's no more room for water in the air. So at lower temperatures, it's harder for water to stay in a vapor state. And once you hit a certain temperature, that water will start to condense, turn from gas into liquid. So, and that specific temperature, based on the capacity, how much water is in the air, is called the dew point. So the fact that we cool by evaporation means that hot and humid conditions interfere with our ability to cool our bodies down. They interfere with the evaporation of perspiration and the way we cool our bodies. Therefore, the temperature we actually feel can be greater than the measured air temperature. And this is why there's something called the heat index. So the heat index gives you a sort of estimated apparent temperature based on the combination of the actual temperature and the humidity. And then you can see here, if conditions are hot and humid, it can be quite dangerous, because you stop being able to cool your body down and basically you cook. That is bad. And you can see the lower the humidity, the higher the temperature outside you can handle. So another way to describe the amount of water in the air is something called the dew point. The dew point is the temperature at which water will start to condense out of the air. It's the temperature at which the air we have right now will start making dew, hence the dew point. So it's the temperature where a sample of air, if you cool it down to that, it will become saturated. So at the dew point, the relative humidity is 100%. Once you cool to the dew point, water will start condensing out of the air. So if you cool below the dew point, you get condensation of moisture, generally, as long as there's something for it to condense on. There's something called supersaturation. We'll mention it later. Now, we're talking about humidity. How do we measure humidity? Well, the traditional way is with something called a psychrometer. The psychrometer consists of two thermometers, one that has a dry bulb and one that has a wet bulb. The wet bulb thermometer is kept wet, so evaporation cools it. So the easier it is for water to evaporate, the more the wet bulb thermometer gets cooled. The drier the air, the easier it is to evaporate. The more cooling the wet bulb has, the bigger the difference between the two temperatures. This is what's called the psychrometer. So the dry bulb measures the actual temperature of the air. The temperature of the wet bulb is depressed, and as a function of the moisture content of the air. And the lower the humidity, the more evaporation occurs, and the more latent heat of evaporation is removed. Therefore, the wet bulb temperature is depressed more. So at 100% humidity, they would be the same temperature. And then the lower the humidity, the lower the wet bulb thermometer temperature. This is the traditional way you measure humidity. The way you measure humidity these days, because it's much easier, faster, and more efficient, is that it turns out the humidity of the air affects the capacitance of the air. So if you set up a capacitor with two parallel plates, the humidity of the air between it affects the capacitance of that capacitor. That's very easy to measure electrically. So these days, humidity is generally almost always measured electrically, and the sensors are tiny. But this is the traditional way, and we will go over how this works. So a traditional psychrometer, there's also a type called a sling psychrometer, which you take out into the field, you set up, and you whip it around, rotating it to quickly stabilize the wet bulb temperature and get your two measurements. And it looks really silly because you're spinning a couple of thermometers around in a big circle. So using psychrometric tables. We'll go over how to use psychrometric tables. There's a few questions on the homework about this, but I'm not going to put any on the test because these just tests or quizzes, because these just take too long to do for tests and quizzes. But there are some homework problems. So if you have a psychrometer, let me. There is on the homework, but I don't think well, there might be a little bit on one of the. Oh, yeah, on the homework online, yeah. You haven't taken the quiz or the test yet. For chapter 19? No. Yeah, you may have done the homework, which is fine. And I was mentioning that there's homework problems about this. There are some homework problems about this, but because these are relatively slow to do, I didn't put them on the test, or I don't think there's any on the quiz. I mean, you need to understand how these work. But you'll have access to the table because you have to look this stuff up in a table. But it's not on the test. So here we have a psychrometer measurement. We want to find the relative humidity, the maximum moisture capacity, the actual moisture content of the dew point. So dry is 80 degrees Fahrenheit. Wet is 73 degrees Fahrenheit. So change is 7 degrees Fahrenheit. So that's the depression. I'm just going to use a delta because it's the standard symbol for change. So here is how you use these tables. These are in your book. At the end of the book, there's a link on the homework problem to these tables. They're in the appendix, I think. So the way you can look these up. So we want to find relative humidity, maximum moisture capacity, actual moisture content, and then dew point. So this table gives you, based on the air temperature of the dry bulb thermometer and the number of degrees of depression of the wet bulb thermometer, the relative humidity, and the maximum moisture content. So the relative humidity, well, the dry bulb temperature is 80 degrees. It is depressed 7 degrees, so 80 and 7. Just make sure I'm in the right row. The relative humidity will be 72% because it's right here. 7 degrees depression, 80 degrees temperature. The maximum moisture capacity is 10.9 grains per cubic foot. The actual moisture capacity, well, it's just going to be 72% of 10.9 grains per cubic foot. So 10.9 times 0.72 gives me 7.85 grains per cubic foot. And then the dew point, you have to look that up in the next table, which is this table. This tells you the dew point given the dry bulb temperature and the wet bulb thermometer value. So 80 degrees and 7 degrees of depression. The dew point is 70 degrees Fahrenheit. So the first table gives you the relative humidity and the maximum moisture content. The actual moisture content is just the relative humidity times the maximum moisture content, well, divided by 100%. So 10.9 times 0.72 gives you 7.85. 7.848 or something, but I rounded it to pretty significant figures. So if we use table H1, we find the relative humidity by looking at the dry bulb temperature in the first column and reading over to the right until you get the column with the measured wet bulb depression, which ends up being 72%. Then we can find the maximum moisture content from table H1, which is 10.9 grains per cubic feet. Ning? Sorry? And then the actual moisture content is just going to be relative humidity times the maximum moisture content. You have to convert from a percentage to a decibel just by dividing by 100. So 72% gives you 0.72 times 10.9 grains per cubic feet gives you 7.8 grains per cubic feet. Yeah, okay, so I'll just match this. Oh, yeah, it would be this too. Sorry. 7.8 grains per cubic. I don't think it's set up to care too much about significant figures. And then the dew point, the settings can be a little weird. So the dew point, you have to use the second table. It's a different table. And on this table, it's just, this is the dry bulb temperature, this is the depression. And it says 70 is the dew point. So you use table H2 to find the dew point temperature by looking at the dry bulb temperature in column 1 and then read over to the right with the measured wet bulb depression. You know that's 70. So if you cool the air down from its starting temperature of 80 degrees down to 70 degrees Fahrenheit without changing the absolute humidity, it will go from 72% humidity to 100% humidity. Here's another example. I guess I'll just do go over here. Here, the dry bulb and wet bulb are 85 and 70. So dry is 85 degrees. Wet is 70 degrees. So the change is 15 degrees. Because 85 minus 70 is 50. So we want to again find relative humidity, maximum moisture capacity, absolute moisture content, and dew point. So we'll go back to these tables. We use the first table for relative humidity, maximum moisture content, and then we can calculate absolute moisture capacity, which is just relative humidity times maximum capacity. So the relative humidity, well, our dry temperature is 85, and our drop is 15. So 85, we have 15 degrees of drop. Our relative humidity is 46. Percent. Our moisture content, our maximum moisture content, well, 85, that will be 12.7 grains per cubic foot. The actual moisture content will be 12.7 grains per cubic foot times 0.46, or 0.46 times 12.7, which is 5.8 grains per cubic foot. And then the dew point, we'll have to go to table H2. The dew point, 85 and 15 degrees of drop. Is 62 degrees. So again, table H1, we find 85 and 15 degrees of drop. We see the humidity is 46%. Table H1, we find 85 degrees, gives us 12.7 grains per cubic foot for maximum moisture content. Actual moisture content is going to be 46% of 12.7. So 0.46 times 12.7, which is 5.8 grains per cubic foot. And then lastly, we use table H2 to find the dew point temperature. Again, 85 degrees, 15 degrees of drop. And we find the dew point is 62 degrees. So that's how you can use the psychrometric tables. Again, these days, humidity is primarily measured electronically. It's just faster and easier. Ugh. And all these are in the slides that you can download. So another important thing we want to measure is what the wind is doing. So an anemometer is a device for measuring wind speed. This is usually done with what's called a cup anemometer, which uses small cups that spin around as they win with the wind that are set up like this. The advantage of this is that this design works no matter which direction the wind is coming from, without having to like reorient or anything. It just spins in the same direction based on how fast the wind is blowing, independent of the direction. And the direction of the wind is indicated with a wind vane. Whereas the wind blows on this, and the pointy end of the wind vane points where the wind is coming from. And wind direction is reported. This is a little bit confusing, but wind direction is pretty much always reported as the direction it is coming from. So a north wind blows from north to south. An east wind blows from east to west, and so on. This can be a little confusing when you try and think about like what direction an actual because if you draw an arrow in the direction of the wind, the direction that arrow is pointing is opposite the direction of the wind direction, because it's the direction the wind comes from that defines the wind direction. Just something you need to keep in mind. And it's because it's traditional, and it also, like north winds are cold because the north is cold, kind of thing. And then the last thing we can measure is precipitation. Typically, rainfall is measured with a simple rain gauge. The US is basically the only country that still reports rainfall in inches. Everybody else uses the metric system. And a rain gauge is really just a tube that you let rain fall into and collect. And it's assumed the rainfall measured in a single rain gauge accurately represents rainfall for the surrounding region. There's slightly more advanced rainfall gauges, which is a funnel going into a skinnier tube, so it's easier to see the levels. Or there are some that actually measure the amount of water that comes out of a funnel to record electronically. Snowfall is reported in depth in inches, and the actual amount of water in the snow depends on the density of the snow, which can vary quite a bit. And snowfall, you have a board. Snow falls on the board, you stick a ruler in. At least that's the traditional way you measure it. Snowfall depth is very variable because it can pile up and such. Now, modern weather observations can be made in more advanced methods. One of the most useful tools we have is that we can use radar, which is radio detecting and ranging. Is widely used today to detect and monitor precipitation, especially severe storms. Basically, and the more advanced version of this is called Doppler radar, where we can measure not only how much water there is, the intensity of precipitation. Basically what it is we send out radio waves that bounce off water droplets in specifically raindrops and come back. And cloud drop, if you set your the wavelength of your radio waves right, you can set it up so that it will ignore. You can differentiate between raindrops and cloud droplets. You can basically set a minimum size to detect. And you send out radio waves, they bounce off the rain, and how much bounces back tells you how much rain there is that is reflecting radio waves. But with Doppler radar, you could also measure how things are moving. You get wind speed information by looking at how the frequency changes. In the exact same way that a radar gun at the top tracing getting your speed from a car works. That also uses the Doppler effect. It bounces a radio wave off your car, and the change in frequency tells you how fast you're going. So Doppler radar allows us to not only measure how much rain there is, but how fast it's moving towards or away from the radar station. And from that information, you can figure out information like how much it's spiraling, which is whether there's the chance for tornado, things like that. You can get wind speed information. You don't only actually get wind speed information about how the wind is moving towards or away from your radar station. Name? So Doppler radar is restricted to information about how fast things are moving towards and away from you. Oh, I should have. Okay, now this should work. Give this a second. It can't tell you anything about something that's moving at right angles sideways from your point of view. That will look exactly the same as something that's not moving but you can actually see it move. So there's sort of there's ways to get that information with other techniques. So here's a short video about Doppler radar. And being very slow to learn.
Hi, this is Sean with the Billings National Weather Service. In this presentation, I will discuss a few weather radar basics. So, why is the Doppler radar important? Well, without it, meteorologists would not be able to see what is going on inside a thunderstorm very well, nor would we be able to forecast the movement of a thunderstorm very precisely. Our warnings would be less accurate, putting more people and property at risk during hazardous weather. In this example, we see a snapshot of Doppler radar data showing circulation at the time of the June 20th, 2010 Billings tornado. The Billings Doppler radar, labeled KBLX, is in the middle of the black circular region towards the left of the radar image, while the circulation is in the white circle. How does the Doppler radar work? The antenna shoots out pulses of electromagnetic energy at specific elevation angles above the ground. When these pulses of energy encounter an object in the atmosphere, such as a raindrop, hailstone, or snowflake, part of the energy pulse bounces off of the object and returns to the receiver. This process is illustrated in the animation. The signal produced by the object is then sent to the signal processor, where it is turned into usable data called base data, which we see as reflectivity and velocity. Reflectivity shows where precipitation is, while velocity information helps us identify rotation and strong winds within a storm, allows us to determine wind speed and direction behind a cold front, and allows us to determine which direction and how fast an object in the atmosphere is moving. Note that what the radar shows us is not necessarily what is reaching the ground. As the radar beam goes out from the radar, it continually rises in elevation. By the time this beam reaches a town such as Ekalaka, it is well over 10,000 feet above the ground. The radar cannot detect precipitation or winds below the beam, which is why we rely on your reports to give us some ground truth. Thanks for joining me. I'll have more details about Doppler weather radar uses in future lessons. Remember, data on our website can be accessed by clicking on the radar image towards the bottom of the main page.
So, the motion of air in the atmosphere, there's a few ways that air can move in the atmosphere. It can either move horizontally or vertically. And horizontal movement of air we refer to as wind, and vertical movement of air, broken down into updrafts and downdrafts, we can refer to as air currents. And the motion of the air is driven by two primary forces: gravity and pressure differences due to temperature variation. It turns out when you heat up air, its pressure changes. And air is being pulled down constantly by gravity. So the voice of gravity is always directed vertically downward. It acts on every gas molecule within the atmosphere, resulting in a greater density of air near the Earth's surface. And that means if you change the density of a packet of air, it will either sink or rise until it gets to the level of other air. And gas pressure and temperature are directly related to each other in the atmosphere. So if there's a temperature variation that exists between two bodies of air, there will be a pressure difference. When a pressure difference exists in the atmosphere, the air will move from a high to a low pressure region. So winds blow from high pressure to low pressure. So if you take a number of pressure measurements all over the place, you can make a map of the pressure over space. And we can map this with something like a topographic map. We can use lines of constant pressure called isobars. Iso means equal, bar is pressure, isobars. So a line of equal pressure is a line on the map, and air movement will not occur along a given isobar because by definition, the pressure difference doesn't exist. Air will be driven perpendicular to isobars. This is ignoring the Coriolis effect because the Coriolis effect makes everything more complicated. But that near the ground, that's going to be the case. So the wind direction is going to be at right angles to the isobar and in the direction of lower pressure. Because you have higher pressure pushing out, and it pushes the air in the direction of the lower pressure. An unequal heating of the Earth's surface leads to thermal circulation. Warmer air expands, gets less dense, rises. Cooler air contracts, gets more dense, sinks, and you get convection cycle. And this causes pressure gradient. So here's a short video about pressure gradients. And the relationship between pressure and temperature is kind of confusing because it's,
We live at the bottom of an ocean of air. Currents in this ocean move masses of gas around, and this movement creates the weather we experience every day. Most of the gas is diatomic nitrogen and oxygen with small amounts of argon, helium, carbon dioxide, and other trace gases mixed with varying amounts of water vapor. All of these gas particles have mass and are pulled towards the Earth by gravity. The weight of the particles in a column of gas above each of us applies a force that we experience as atmospheric pressure, which is simply the weight of the column of gas above a specific area. Air pressure is greatest at the ground and decreases with altitude, both because the column of air gets shorter with increasing altitude and the density of the gas particles decrease with altitude, meaning there are less gas particles per unit volume at high altitude compared to ground level. As individual gas particles warm, they take up more space, causing the gas to be less dense. Water vapor also decreases the density of air, so increasing water vapor in the atmosphere decreases atmospheric pressure. As air gets warmer and gains water vapor, atmospheric pressure decreases. Warm, wet air is less dense than cool, dry air. And atmospheric pressure decreases as gas in the atmosphere warms and as humidity increases. Atmospheric pressure increases as gas in the atmosphere cools and loses water vapor to precipitation. Uneven heating and varying amounts of water vapor in the atmosphere results in regions of high and low pressure. These pressure differentials cause air to move along the ground from regions of high pressure to regions of lower pressure. We experience these air currents as wind. The force driving the currents caused by differences in pressure between two regions is called pressure gradient force. Air masses moved by pressure gradient force transfer heat by convection as cooler gas particles move into regions containing warmer gas particles. This is similar to the smaller, more contained convection cycles present in a room heated from one side, where warm air rises from a heat source, moves across the ceiling, cooling as it goes. Once cooled, it sinks and the cool air returns along the ground towards the heat source. Although it is not as simple in the atmosphere because the system is more open, so the rising and falling air masses cause movement in many directions. The movement of air up around regions of low pressure cause air masses to converge near the ground and diverge high up in the troposphere. The opposite happens around regions of high pressure, where air currents diverge near the ground and converge in the upper atmosphere. Because we live on a rotating planet, wind does not blow in straight lines directly between regions of high and low pressure. Actual wind direction is determined by how air movements driven by pressure gradient forces are deflected by the Coriolis effect.
now, certain places have daily convection cycles because of unequal heating and cooling. The classic example is over land and water. Land warms up and cools down much faster than water because the heat capacity of water is enormous. So during the day, the land will heat up faster than the adjacent body of water because it has a low capacity for storing heat. This is also why in the summer, the beach is burning hot and the water is freezing cold. The land will heat up faster than the adjacent body of water because it has a low capacity for storing heat. The air above the land will warm, expand, and rise. It will flow in, so air will flow in from the sea to replace it, and you get a convection cycle. This is referred to as a sea breeze because all winds are named based on where they come from. So this is a sea breeze because you're getting wind in from the sea. At night, you'll get the opposite, a land breeze. The land will cool off faster than the adjacent water, which has a higher capacity for storing heat. The air above the land will cool, contract, and descend, and air will flow from the land to the sea, and the daytime cycle gets reversed. This is called a land breeze, where the land ends up colder than the water, because it varies more. Here's a short video about land and sea breezes.
I very much enjoy going to the beach. One thing that I can count on almost every day is that sometime during the day, it's going to get windy. But why do we have these sea breezes at the beach? Welcome to Moo Moo Math and Science and Land and Sea Breezes. Land and sea breezes are considered local winds because they only travel a short distance. But what causes them? Like other winds, these local winds are a result of unequal heating of our atmosphere. Land and water warm up and cool off at different rates. This statement will help you understand land and sea breezes. It is, land always wins. What this means is that land both warms up faster than water and cools down faster than water. This unequal heating results in winds. A couple more statements will help. Warm air is less dense than cold air and will rise and create low pressure. Cold air is more dense than warm air and will sink, and this creates high pressure. Air will always move from high pressure to low pressure. In other words, high to low is the only way the atmosphere will go. So as the sun rises and begins to warm the beach in the morning, the land begins to warm up faster than the water. A low pressure system is created over the land because it is warmer. The water is colder and has a high pressure. As a result, the wind will blow from the sea to the land. Wind is named from where it is flowing from, so this is a sea breeze because it's flowing from the sea. At night, the beach begins to cool down, and the land cools down more quickly than the sea. As a result, the high pressure is now over the cooler land. The water is warmer and has lower pressure. The wind flows from the high pressure over the land to the low pressure over the water. It is flowing from land, so it is considered a land breeze. So remember, land always wins, and high to low is the only way the atmosphere will go. Thanks for watching, and Moo Moo Math uploads a new math and science video every day. Please subscribe and share.
So we've talked about the general force that pushes air around. Unfortunately, there is one major complication that makes things a little more confusing. This is the Coriolis effect. And this is an effect caused by the fact that we are on a spinning ball. The Coriolis force or the Coriolis effect is due to the fact that we are in a rotating reference frame. So the Coriolis effect is arguably not a true force. What a true force is and whether in reference frame forces count gets even more confusing as you get more advanced. You might as well treat this is one of those ones where it's a real force. It's not a real force. Oh, it is a real force. But yeah, it's not considered a true force in a lot of cases because it's caused by the fact that you're in this rotating reference frame. It's a result of the fact that you're in a rotating frame of reference. So it is considered a pseudo force. But it acts just like a force. There's rules for it. They work. It's considered a pseudo force and helps to explain its effects, so the laws of motion will be consistent. It's basically a correction for the fact that we're on a spinning ball, but don't notice the fact that we're spinning. So what happens is projectiles, and wind counts as a projectile in this context, get deflected. They get deflected to the right in the northern hemisphere and to the left in the southern hemisphere because they're upside down. As observed in the direction of motion. So if I fire a projectile and I watch it, it will appear to bend to the right. it's not gonna happen in the kind of range that we normally see, but it's something you have to take into account if you're doing something that's over a long distance and very quickly. For example, you have to correct for the Coriolis effect when you're aiming your guns on your ship. So an observer in space over the North Pole will watch a projectile travel in a straight line. But the Earth rotates underneath that straight line. So to an observer on Earth, it appears to veer to the right. And this same effect happens no matter which direction you fire the projectile. You get an apparent veer to the right, caused by the rotation of the Earth. It can be caused by the fact that, it was actually moving faster because it was closer to the, because it was further from the center of rotation and other things. But it always works out to be a bend to the right. This is the Coriolis force. And it's a force, it's proportional to how fast you're going. And it always, turns you in the northern hemisphere to the right. And in the southern hemisphere, it turns you to the left. And this is why large weather things spin in circles. And they spin in opposite directions in the northern and southern hemisphere because the wind gets deflected. It is very hard to observe on a small scale.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
So as air travels into a low pressure area, it gets, in the northern hemisphere, deflected to the right, and you effectively get rotation counterclockwise, as shown here. as air travels out of a high pressure area, it gets deflected to the right, and you effectively get clockwise rotation, as shown here. So in a cyclone, which is a low pressure area, in the northern hemisphere, you get counterclockwise rotation. And in an anticyclone, a high pressure area, you get clockwise rotation in the northern hemisphere. In the southern hemisphere, everything switches direction. That's because, from the point of view, it's the same direction, it's just upside down, is the way you can think about it. It looks like it's rotating the other direction because now we're looking at it from the other side. That is why the directions switch between the northern and southern hemisphere. So high pressure air mass descends, it results in a clockwise rotation. It also tends to cool. Low pressure air mass rises, resulting in a counterclockwise rotation, and things heat up. Now, because there is a temperature difference between the equator and the poles, because one gets more light than the other, there's a giant circulation over the whole Earth. You know, warm air rises, the equator is warmer than the poles, so at the equator air rises, at the poles air sinks. But because the Earth is spinning, and there is a Coriolis effect, you don't get one big loop. So if the Earth wasn't spinning, you just get one big loop where it would rise at the equator and sink at the poles. But because the Earth is splitting, that splits into a series of smaller loops. The same thing happens on other planets. This is actually why you can see stripes on Jupiter. Jupiter is spinning faster and is bigger, so it has more cells than Earth does. So there's more visible, but you can see visible stripes from it. That's what causes the stripes. So Earth has 3 cells between the equator and the North Pole. You have warm air rising at the equator, sinking at the subtropical high Horse latitudes with the northeast trade winds in between. Then that sinking air at the subtropical high latitudes moves north and drives the westerlies and rises at the subpolar low. And that rises up and sinks at the polar high, causing the polar easterlies. So there's a series of winds in opposite directions because of the Coriolis effect, because they're, air flowing from the, wind flowing from the high subtropical high Horse latitudes to the equator is going south and gets bent to flow east. It's bent to flow to point, bends to the right, and you get wind from the northeast. That's the northeast trade winds. And over most of the US, the large scale circulation is moving air from the subtropical high Horse latitudes to the subpolar low, and you get winds coming nominally from the south, which bend to become westerlies. So and this is actually what drove trade across the Atlantic, and what made trade across the Atlantic so easy. Because you could go north to hit the westerlies to travel to Europe, and go south to hit the northeast trade winds to go back to the Americas. It was very easy to go back and forth, but you just had to go north or south along the Atlantic. So many local variations occur within these cells. These prevailing winds of the semi-permanent circulation structure are an important influence in general weather movement around the globe. And this is why, in general, in the US, because we're in the westerlies, weather moves from west to east. Not always, but in general. So weather patterns in the lower 48 states of the US serve as an example. The region lies generally in the westerlies wind zone, and so weather systems are going to move from west to east across the country because they're driven by that primary wind. Now, there are also what are called jet streams. These are high-level winds, high altitude winds that are fast moving ravens or rivers of air located up very high in the upper troposphere. They are formed along the upper boundaries of these warm and cold air masses. And study of these began around World War II. They were first discovered by a Japanese scientist, and during World War, and more serious study began during World War II when high-flying aircraft encountered them. The Japanese did attempt to weaponize them by sending balloons into jet streams and across the Pacific to drop things on the US. It worked very well because it was basically impossible to aim. But a jet stream continuously meanders throughout the year, and it can affect the severity of winter. So if you've heard of the polar vortex, that is a jet stream. That's a jet stream around the North Pole. And how it moves can affect our weather during the winter, for example. So this is the polar jet. There's the subtropical jet. And then we have the similar ones in the southern hemisphere. So the polar vortex is the polar jet. And it's a vortex because it's a big loop going around in a circle. And it travels from eastward. All the jet streams travel east. Clouds are buoyant masses composed of visible water droplets or ice crystals. If you can see it, it's liquid or iced. Water vapor is invisible. Now, clouds are of particular interest to anyone studying the weather because their size, shape, and behavior are some of the few visible keys to what's going on in the atmosphere. Because the rest of the atmosphere is transparent and thus very hard to see what is going on. Also, they're made of water, which is important. We care about precipitation. The clouds are classified according to their shape, appearance, and altitude. There are 4 basic root names used to describe a cloud's shape and appearance. These are cirrus, which are wispy fibrous forms. It means like hair. Cumulus, which are billowy round forms. It means like pile or something like that. Stratus, which is stratified or layered forms. And nimbus, which is a cloud from which precipitation is occurring or threatens to occur. You can identify nimbus clouds generally because they are much darker, because they're about to dump a bunch of rain, water in.
And they send much higher into the atmosphere.
Depends on the type of nimbus, but yes, there are.
I'm thinking cumulonimbus.
Cumulonimbus is yes, but there's also like stratonimbus.
Yes, those don't affect.
Clouds can be classified according to their height as well. High clouds get a prefix of cirrus. So those wispy cirrus clouds only occur very high in the atmosphere. So other shapes of clouds that occur at the same height also get called cirrus. So these are cirrus, which are these thin wispy clouds, and then cirrocumulus, which are like lumpy clouds very high, and cirrostratus, which are sheets very high. Middle clouds are called alto, because alto means middle. You can have altostratus, which is sheets in middle heights from 1.8 to 6 kilometers, and altocumulus, which are lumpy clouds in middle heights. And then low clouds from the ground level to about 1.8 kilometers are things like stratus, stratocumulus, which is sort of a mixture of sheet and lumpy, nimbostratus, which is that sheet covering the sky that is dark and is threatening to rain on you, and then things like fog. Fog is technically a cloud that touches the ground. And then there are also clouds of vertical development that cut through layers. And cumulus clouds can be like that. And cumulonimbus clouds are very, very tall. And those are thunderstorm clouds. Those are those hammerhead thunderstorm clouds with the amble top. So here is an example of a cloud with vertical development. You can see how it's very tall and it flattens out at the top because what's happening is the air is rising up until it hits a temperature that matches the amounts it's expanded, and then it travels sideways. So true water vapor in the air is invisible. To see water, it has to condense into droplets. So the steam you see over a pot you're boiling or from a cup of tea, that is actually little droplets of water. Which is why if an actual steam pipe bursts, you can't see the steam, and it's incredibly dangerous. Now, condensation requires that a given mass of air needs to be cooled down to the dew point temperature. And when the dew point temperature is reached, the water vapor will condense into fine droplets and form a cloud. It is theoretically possible for you to supercool a package of air so it gets below its dew point temperature. But for that to happen, there has to be nothing in it that it can condense on, and that's actually pretty rare. So water droplets form around condensation nuclei, like little bits of salt, little pollen, bits of stuff in the air. And there's usually stuff around. And air within the troposphere is constantly moving. And when an air mass is cooled sufficiently, cloud formation can take place. And cloud formation is associated with the vertical movement of air because the temperature of the troposphere drops with altitude. And as a packet of air rises up, it cools down. And eventually it will cool below the dew point and condense. So in general, cloud formation is due to vertical air motion, currents, and clouds are shaped by horizontal air motion, winds. So you have a packet of warm, wet air, it rises up, eventually it steadily cools as it rises because it expands as the pressure decreases, basically. And eventually it hits a point where it's below its dew point and it starts to form a cloud. And then the rate at which it cools as it rises will change because it's now condensing water out and that heats it. And eventually it'll hit a point where it matches the air temperature and it will level off. So the bottom of the cloud is where rising air is hitting the dew point and condensing, and the top of the cloud is where the rising air ends up the same temperature as the air around it, so it stops rising up. So here's a video about hot clouds.
Most of the time, if we pay attention to clouds at all, it's because of their effect on our local weather. Or maybe it's because they make a sunset prettier. But what you might not know is that clouds affect us every day, even if we're staring at a clear blue sky. The clouds we see when we look out the window are important components of a complex global weather system. They play a key role in Earth's water cycle, carrying huge amounts of fresh water and dropping it as precipitation. And depending on their properties and where and when they form, clouds can have dramatic effects on our climate, influencing the locations and severity of floods and droughts, and even the temperature of our planet as a whole. So by understanding clouds, we can better predict severe storms, the global distribution of fresh water, and the course of climate change. But what exactly are clouds, and how do they form? All clouds share the same basic ingredient: water. They're made up of water droplets or ice crystals that have formed from water vapor in the atmosphere. Although you can't see it or feel it, the air around us contains water even on the clearest summer day. The main sources of this vapor are evaporation, which is the escape of water molecules from the surface of oceans, lakes, and soil, and transpiration, the release of water by plants. As the sun warms Earth's surface, heat is transferred into the atmosphere along with water vapor. The warmer the air, the more moisture it can hold. But warm air doesn't usually stay near the surface for long. Like a hot air balloon, it rises. As it does, it cools. The colder the air becomes, the less water vapor it's able to hold. If the air becomes cold enough, it reaches a state called supersaturation, which causes some of the water vapor to transition back to a liquid or solid state. Water molecules in the vapor form around tiny particles of dust, ice, sea salt, and pollution suspended in the atmosphere. These particles, called condensation nuclei, serve as the starting point for the formation of water droplets and ice crystals. With this final step repeated billions and billions of times, the water that's been in the atmosphere all along is suddenly visible. And a cloud is born. While we can now see the cloud, the individual droplets or ice crystals are tiny, which is why they remain airborne. But they can combine to form larger drops or crystals. And if they become large enough and too heavy to stay aloft, they'll fall as rain, snow, sleet, or hail back to Earth's surface, where the water in them came from originally.
And here's a video about the shapes of clouds. I think we'll stop after this one. Catch up.
Clouds are an ever-changing aspect of weather, and clouds can often be a great visual indicator of certain weather patterns, and they can even act as a harbinger of upcoming weather conditions. In this brief weather tutorial, we will discuss 4 primary types of clouds, as well as some combinations or hybrids within these categories. We'll show some specific examples of each, and we'll also look at some of the weather elements associated with these different cloud types. Clouds are categorized by their structural characteristics and the height in the atmosphere at which they develop. The 4 main forms of clouds that we'll talk about are cirriform, cumuloform, stratoform, and nimboform. There can be different combinations or hybrids of each of these cloud types. Cirrus clouds are high-level clouds that typically form between 16,000 and about 50,000 feet above the Earth's surface. And the Latin word cirro means curl of hair, and many times cirrus clouds can mimic curls of hair due to the thin, wispy structure that they exhibit. Cirro can also be used as a prefix to describe high-level clouds. Cirrus clouds are composed of tiny ice crystals suspended in the upper parts of the troposphere, which is the layer of the atmosphere where all weather occurs. And cirrus clouds are often thought of as indirect indicators of weather patterns. Sometimes they may accompany a strong jet stream in the upper atmosphere. And cirrus clouds can also be seen preceding surface fronts by more than a day or two. Cumulus clouds might be one of the more recognizable cloud types. Cumulo is Latin for heap or pile, and cumulus clouds can often look detached or isolated from other clouds, and they'll often appear as fluffy white cotton balls or perhaps even cauliflower. These clouds are considered low-level clouds, usually forming between a few hundred to a few thousand feet above the Earth's surface. In the desert Southwest and much of New Mexico, these cloud bases will often form at even higher levels than other parts of the country due to the warm and arid conditions within the Southwest. Stratiform clouds, or layer clouds, often appear as a sheet or layer of cloud that exhibits little definition or features. In other words, they will typically appear as a hazy white or gray mass. Stratus clouds are primarily thought of as low clouds, but they can also be observed in the middle to upper parts of the atmosphere as well. Mid-level stratus clouds are referred to as altostratus, and high-level stratus clouds are commonly identified as cirrostratus. Nimboform clouds are also representative of a hybrid or combination of different cloud categories. Nimbo is Latin for rain. The 2 common nimboform cloud types are nimbostratus and cumulonimbus. As you can probably guess, nimbostratus are layered clouds producing rain precipitation. These clouds can extend into the middle to upper parts of the troposphere, but they are typically only seen in the lower parts since they will usually obscure any clouds above. Cumulonimbus are also a unique hybrid of cloud that extends from the lower to the upper parts of the troposphere and are otherwise known as thunderstorm clouds. We briefly mentioned cirrostratus, but another high-level cloud is cirrocumulus. These are similar to altocumulus, the difference being that altocumulus form in the mid-levels of the troposphere, while cirrocumulus clouds are in the highest part of the troposphere. Altocumulus clouds have some variations of their own. One such variation that frequents New Mexico is the altocumulus standing lenticular, sometimes simply referred to as lenticular linnies, or even wave clouds. These clouds are common on the leeward side of topographical barriers, such as mountains, where a stable layer of air is then found above the crest or peaks of the topography. Stratocumulus clouds are another combination of two previously mentioned categories, stratus and cumulus. So we've discussed several types of clouds. We hope that you've learned something about clouds, and maybe you can scan the skies next time you step outside and identify some cloud types on your own. For more information, refer to the National Weather Service, including the Jetstream website, where you can learn more about clouds and see more cloud diagrams and imagery.
Well, that is all for today. Here's a guide to the classification of different types of clouds. We will finish this up next week. So you're free to go, because it's the end of class. Yeah, it can affect, well, it can, the particulates that release can act as, well, so the particulates released by factories can act as nucleation sites for condensation. They can also be something like soap factory. A lot of what that's probably releasing is actually water. So, if you see a lot of white coming out, often that's just a lot of water coming out. I don't know exactly what the soap factory is coming out. I mean, I know about it. I drive past it every day, but
They don't usually put out stuff that stays in the atmosphere.
they don't put out a lot of stuff that stays in the atmosphere. I mean, there's more indirect effects. I think that then clouds sort of act as a way to clean out particulate matter from the atmosphere as well, because water condenses and then it turns into rain and it falls. Yeah, it's part of it. I mean, generally rain is cleaner. Depends.